Now we are going to talk about Bayesian computation. This is a very important lecture in the following sense, very important unit. The crux of the Bayesian statistics lays in how to compute the posterior, how to compute the Bayes estimators, and that is often not very straightforward and very easy. So one of the strengths of Bayesian statistics is that in recent years, this Bayesian computation got very advanced with the rise of Markov chain Monte Carlo methods, so that popularity and the widespread use is attributed to the ease of the computation. We are going in this unit to talk about two approaches to Bayesian computation. First one is classical numerical approach, in which the integrals are going to be done numerically, and the second, more important, is Markov chain Monte Carlo. We are not going to go to the nitty-gritty details of setting the Markov chain Monte Carlo calculation method, but simply for you to get a feel what is below the hood, and to understand when we use the software, let's say Winbugs, what is going on behind the scenes. The first one is numerical approaches in Bayesian computation. We will start with sort of numerical integration. People often say that in classical statistics, the most important mathematical tool is optimization, because many rules are optimal in some sense, least square estimators, minimax rules, and so on and so forth. While in Bayesian statistics, the key operation is integration. If you take a look at the Bayes theorem that we covered in the previous units, you see that the posterior is conceptually easy. It is the product of the likelihood of the model, f of x given theta, times the prior, and divided by m of x, which is marginal. The difficulty is essentially in the marginal. It would be quite easy to have the posterior equal to the likelihood times prior, and indeed, this is the proportional to the likelihood times prior. But this product is not a density. It has to be normalized to be a density, and that normalizing constant is the marginal. Now, when you look at the marginal, that is essentially the integral of the likelihood times prior. It looks simple, but given the complex experiment, many data points, this integral often could be unfeasible, undoable, even with numerical methods. In the previous saw a way around it. If the problem was conjugate, if the likelihood and prior formed the conjugate pair, we did not need to integrate. We find the product from the form of product, let's say this sort of kernel. We conclude what the distribution is and simply normalize by the fact that we know what distribution it is. We saw this in binomial beta and then Poisson gamma and so on and so forth. However, for non-conjugate cases, typically we need to numerically compute the posterior, either by numerical integration for marginal or by random sampling, which is going to be discussed. As an example, let's take a look at the case in which there is an observation coming from normal distribution. The location, the mean of normal distribution theta, is not known, it is theta. Variance is known, it is 1, and we put the prior on theta, which is Cauchy. So the likelihood is proportional to the e to the minus 1/2 x minus theta, the quantity squared, because this is the part that contains the parameter of interest, and the prior is proportional to 1 over 1 plus theta squared, the Cauchy distribution. So to find the marginal, we need to find the integral of this exponential times coming from the likelihood times this part coming from the prior. However, this integral is not solvable in terms of the elementary functions. And what do we need to do is to do numerical integration. Recall that Bayes estimator can be expressed as the ratio of two integrals. But again, these integrals are the marginal and this likelihood times prior times theta in the numerator. So here, in this case, we have the quite complex integral to calculate. We are going to do this using numerical integration. Before doing that, I mentioned that you can do this using sampling. How you can do this using sampling? You can do it in two ways. Essentially, to sample either from the likelihood or from the prior. And let's take a look. So if I'm having the integral of this kind, I can think about as follows. If I sample thetas from normal distribution with mean x and variance 1, that would be taking care about this part here. The normalizing constants 1 over square root of 2 pi cancelled from the numerator and denominator. We can add those. If I sample thetas from normal distribution with x and 1, then this integral becomes empirically close to the average of these sampled values as ratio of these two functions. The reason for that is simply if I have the integral of f of x, g of x, dx, and f is a density, and that could be sort of expectation of g of x when x has distribution f. This, if I can sample from distribution f, x1 up to xn, then this integral is close to 1 over n summation of g of xi. So this is what we are using in this case. We are thinking about this to be our density, f, and then we are having function g to be theta over 1 plus theta squared, or 1 over 1 plus theta squared in the denominator, and then approximating integral with these finite sums. Other way could be the following. I can think about sampling from Cauchy distribution, and then approximating the interval, Cauchy 0, 1, and approximating the integral with the values of this function g now. In both cases, you get approximation to the ratio of two integrals, actually to the base rule. So let's take a look how this works in simulation. I'm going to discuss this norcow.m that calculates base rule evaluated at value 2. The example is going to be in Octave or MATLAB if you have access to MATLAB. And later you can check how well you did this base rule at 2 using Wimbugs. We can also check in a moment numerical integration by approximated integration methods and find that actually this delta 2 is up to some precision equals 0.28219 and so on and so forth. So we'll see how close we get to this exact value.